Day 134, capacitors, example number 3. Here we have a complete circuit. It's capacitors with a battery. But the technique is a lot like number 2, where we need to simplify this circuit first before we can proceed to figure out what the charge is on each capacitor. So there'll be a few extra steps at the end. Anyway, by practice and help in class, you'll get the knack of where to look first. Where is the series and where is the parallel parts of the circuit? Well, here the 6 and the 12 are in series with each other. That's a one pathway where they are quote-unquote in a row, so they'll be in series. We'll be combining those first. And bottom line is, when I combine that, my new diagram will look something like this. Here's the diagram. But we need to combine the 6 and the 12 by using the rules of capacitor combinations for a series. What we need to do is 1 over C total for that combination equals 1 over 6 plus 1 over 12. Put that into your calculator and you end up with 4 nanofarads. By the way, nano is 10 to the negative 9th. Alright, now what we have, if you look at this, the 20, the 14, and the 4 are in parallel with each other. Those are 3 pathways all connected together. So we can combine those 3 capacitors by the rule of series or parallel combinations. That's the easier rule, and that's simply just arithmetic addition, 20 plus 14 plus 4, which is 38 nanofarads. So let me draw that for you. There we go. We've replaced the 3 capacitors that are in parallel with the replacement equivalent resistance. A 38 nanofarad capacitor in that position will act as a collective 20, 14, and 4 in parallel, would be performing the same function. We have one step left, and that is to combine the 5 and the 38. Question is, are they in series or parallel? Well, they are in series. They're in a one pathway around this single loop, so we need to use the rule for series, which again is 1 over C total, or C equivalent, equals 1 over 5 plus 1 over 38. Plug it into your calculator, and it comes out to be 4.4 nanofarads. So I'll draw that. Simplifying the diagram is pretty much half the problem. We've gotten down to one single capacitor, which basically will function like all the other ones from the original diagram, which had 5 capacitors. But this is just a tool for solving the problem being, what is the charge on each of the original capacitors? It comes down to the equation C equals Q over V. What we'll be doing now is applying that equation essentially about 8 or 9 times to each particular capacitor, going backwards now from the simplified diagrams all the way backwards to the original diagram. For example, this last diagram with the 4.4 nanofarad capacitor, we simply plug in the capacitance. We're plugging into that blue equation there, C equals Q over V. We know V is 10, and the capacitance C is 4.4 nanofarads. I'll do that in blue. So I basically have 4.4 nanofarads equals Q, which I'm looking for, over 10 volts. Once again, when I multiply the 10 volts times farads, that will give me coulombs, and it gives me 44 nanocoulombs equals Q. That's the charge on this capacitor here, the simplified capacitor. It's 44 nanocoulombs. Now, one thing to keep track of here is every capacitor has 3 values, the C, the Q, and the V. Its capacitance is its capacity to store charge, Q is the charge it actually stores, and V is the potential difference, the voltage that is, as we would say, being applied to that capacitor to charge it. It's the energy source, so to speak. So what you do now is you take these concepts and you work backwards. So you go from this last diagram with the 44 nanocoulombs in blue, and you go backwards to the previous one that gave rise to the simplified one, and you see the 38 and the 5 nanofarad capacitors in series that's simplified to the 4.4 nanofarad. So there's some connection to the 4.4 nanofarad capacitor, and the connection is, if you look back at the rules, it's this: two capacitors in series have the same charge as each other, and they have the same charge as the capacitor that replaces it. In other words, both of these capacitors are have 44 nanocoulombs of charge. All right, so you write that down and you look at that diagram now on the left-hand side here, and what you want to do is figure out the voltage for each of those. And it's not 10 volts now. 10 volts is the voltage for the entire circuit, but now what you'll find out is that it splits up or shares between the two capacitors in this case, and I'll explain that more as I go along here. But basically right now it's really a matter of applying that blue equation over there, which now I'll use a black marker, applying C equals Q over V to each of these two capacitors over here on the left hand side. In other words, if I apply C equals Q over V, and what I'm looking for now for each of these two capacitors is the V. I know in blue the charge is 44 nanocoulombs for this 5 nanofarad capacitor. The 5 nanofarads is the capacitance. So what I'm going to be doing is using this equation over and over again, but I'm going to run out of space, so I'm just going to kind of circle it right now and have you imagine I'm plugging in 5 nanofarads for C and 44 nanocoulombs for Q. I'm going to calculate V. So when I plug those in there, go to my calculator, I end up with 8.8 volts for that particular capacitor, and I'm going to write that down. And when you're doing these for homework, the main thing that I'm going to grade, homework and test, are your diagrams. You can skip a few of the steps that right now, for example, I didn't show the plug-in. I'm not showing you plugging in the 5 nanofarads and the 44 nanocoulombs and then calculating with my calculator to give me 8.8 volts. So what I'll be doing mostly when I grade these is looking at your diagrams to make sure you have a completed diagrams, and then see if you have jotted down by each capacitor 3 values. The 3 values being C, Q, and V. For example now, the 38 nanofarad capacitor over there on the very left-hand side with the 44 nanocoulombs of charge, I plug that once again into that equation that I have in black here. Plug in the 38 nanofarads for C, the 44 nanocoulombs for Q, and run my calculator. I end up with 1.2 volts for that particular capacitor. So I'm going to write that down, 1.2 volts, and I'm going to allow you to do that on the actual homework or test. Now one check you have is this. If you take the 8.8 volts and the 1.2 volts, what do you notice when you add them up? Well, 8.8 volts plus 1.2 volts is 10 volts. And if you look back at the rules for capacitors that are in series, it tells you in those rules, on that rule sheet, that they will have the same charge as each other, but their voltages will add up to the total voltage, in this case 10 volts. So that's a check that you have on your results here as you go along. Now, here's probably the trickiest step of all. I'm going to take my information from this diagram that I just solved and go to the upper right-hand diagram, which is the one that came before this one. And here's how this works. Bottom line is the 5 nanofarad capacitor is completed. I'm done with that one. I don't need to do any more. I'm going to circle that for now. You don't need to circle it. But I'm not going to do anything more with that when I have all its values. It has 3 values. Every capacitor has a C, a Q, and a V. And I know all 3 of those from that diagram on the left there. So I don't need to do anything more with that capacitor. I'm just going to leave it alone. Now, in this diagram on the upper right, I have 3 capacitors in parallel. Here's the key rule here. If you look at the rule sheet for capacitors in parallel, capacitors in parallel all have the same voltage. In this case, they're each 1.2 volts. I'll jot that down. 1.2 volts, 1.2 volts, 1.2 volts. Now, where did I get that 1.2 from? I didn't pull it out of thin air. Well, I pulled it from the previous diagram over there on the left. I just calculated it a few minutes ago by that 38 nanofarad capacitor down there on the left of this diagram. It has 1.2 volts. It is the replacement capacitor for the three capacitors in parallel, the 20, the 14, and the 4, added up to the 38 nanofarads. That 38 nanofarad capacitor has a 1.2 volt potential difference, and that's what all three in parallel have as well. Once again, it's one of these rules that's so simple, but we can forget. Let me recap the two simple rules. The simple rules are, in parallel, all elements, all capacitors have the same voltage. In series, they all have the same charge. These three capacitors now that we're dealing with in the upper right-hand diagram will have different charges. They have different capacitance, same voltage, but different charges as each other. So how do I now figure out the charge? Well, once again, you plug into the equation C equals Q over V. I'll do one of them for you, but essentially I'm out of space, and you don't need to show this computation, but I'll take this one on the left, the 20 nanofarad capacitor. I'm just going to plug in a C equals Q over V. So that's what you're doing basically over and over again, applying that little simple definition of capacitance to each of the capacitors in the circuit that you're dealing with here. The capacitance here is 20 nanofarads equals Q, what we're looking for, divided by the 1.2 volts. So if I plug that all in, I end up with 24 nanocoulombs. 24 nanocoulombs. That's the charge on that capacitor. So I'll write that in the diagram. 24 nanocoulombs. All right, and I'll do that for the other two capacitors that are in parallel with that particular capacitor. I plug in the 14 nanofarads equals Q over 1.2. That comes out to be essentially 16.8 nanocoulombs. And then finally, the last 4 nanofarad capacitor comes out to be 4.8 nanocoulombs. Now the check on this, in that diagram in the upper right-hand corner now, the one I just finished, is I take those three charges, the 24 nanocoulombs, the 16.8 nanocoulombs, the 4.8 nanocoulombs. If I add those all together, what I should get is 44 nanocoulombs. And I actually get 44.6, which is a little high, simply because the 1.2 volts was rounded up from like 1.16 or something like that. Bottom line is, the check though is close, and it would be perfect if we went to 12 sig figs, which we're not going to do because that's not realistic. 24 nanocoulombs plus 16.8 nanocoulombs plus 4.8 nanocoulombs gives you essentially 44 nanocoulombs. That's your check. All right, now we're actually done with 3 of the 5 capacitors. The 5 nanofarad capacitor was done earlier, but now the 20 and the 14 are done. We know all their values. What's not done yet now is the 6 and the 12 nanofarad capacitors. So we're going to keep working backwards here to the 6 and the 12. So you got to ask yourself, going back to the first diagram there in red, the 6 and the 12 nanofarad, they're in series. What's true of two capacitors in series? If you look at the rules, in series, the two capacitors have the same charge as each other. Not the same voltage, the same charge. And how do you know what their charge is? Well, their charge is the same as their replacement capacitor, which in this case was the 4.8 nanocoulombs. In other words, this guy is 4.8 nanocoulombs, and this one is 4.8 nanocoulombs. That's the charge on each one of those. They have the same charge as each other, the same as their 4 nanofarad replacement capacitor. That's a very key rule. It's an easy rule, but you got to be careful about applying it. All right, now we got to go back and plug into our C equals Q over V equation. And I have it in boxes all over the place here, but right below here, C equals Q over V. I have C for each of these capacitors, and I'll plug into this black equation right here below one time. Let's do the 12 nanofarad capacitor. I'm going to plug in 12 nanofarads equals my charge, 4.8 nanocoulombs, over V. Computing this, I end up with V equals 0.4 volts. So this comes out to be 0.4 volts. And if I apply the same equation, plug into the same equation for the 6 nanofarad capacitor, I end up with the 6 nanofarad capacitor coming out with 0.8 volts. I actually didn't need to do this in this problem, but that's 0.8 volts. But the check here is 0.8 plus 0.4 is what? Well, it's 1.2 volts, because in series the voltages need to add up to the overall voltage for that particular combination in series. Actually, the problem didn't ask me to find the voltage for those two capacitors, but I wanted to just show you that you could do that. I do have all the charges labeled by all the capacitors. If you look around here, and that's what I was asked to do. I have them all labeled in blue, the charges on the diagrams, and those would be my answers to these problems. So there you have it, simplifying a capacitor network circuit and finding out the charges and voltages for all the capacitors involved. You could also find the energy stored in each capacitor, the overall energy stored in the entire system. But you can see that the problems can be very involved, but you have to be very methodical. Draw the diagrams. Please draw the diagrams. You don't need to show as much work, but show a little bit of work, but especially put the answers and put your values by each capacitor. It's 3 important conceptual calculations: the capacitance, the voltage, and the charge on each of the capacitors, some of which will be given, obviously, but the rest we're calculating.